You don't actually understand the Big Bang Theory because what they teach in schools is wrong. I know this because I just got my degree in physics and what they taught us isn't actually what most physicists believe. When I started writing this video, I basically just wanted to explain what the Big Bang was and prove anyone who didn't believe it wrong. But it turns out I was wrong. Most physicists today no longer believe that the Big Bang was the beginning of the universe. Ultimately, I just want to answer the question that I think everyone has about the Big Bang Theory. What was it that actually banged? Was it a singularity? Nothing? What? So let's get to the bottom of this together, and please enter this video with an open mind. Clear all your beliefs about the Big Bang, and I'm sure you'll have your mind blown. Long before modern science had been created, humans looked to the stars and wondered about our place in the universe. There were seemingly infinite descriptions of how the universe came to be, hundreds of gods with their own creationist stories. The Greek atomists believed that the universe was infinite in space and time. The Hindus, Stoics, and Buddhists all believed that the universe went through cycles of creation and destruction. And then in 1687, 44-year-old Isaac Newton published his now famous Principia. In it, he showed that the same laws that described motion here on Earth are true across the universe as a whole. Newton's gravity was born. But there was a problem. If his universal law of gravity were true and every object with mass would attract one another, then surely this force would cause the universe to simply collapse in on itself. Newton borrowed his solution from the Greeks. He basically said that the universe were infinite with no center, and so the matter wouldn't collapse together as the unseen planets and stars would balance the entire system perfectly. Our first model for the universe was born, the static universe. Newton's description of the universe was not only infinite in space, but also in time. Newton was a Christian and therefore believed that his God may have created the universe, but didn't do so at any point in time. This idea of the static universe became widely accepted. That was until some people realized it had a problem. When people looked up to the sky at night, they saw bright spots of light coming from stars and large expanses of darkness. But if the universe were really infinite and eternal, as described by Newton, you should be able to look in any direction and see something. A star, a galaxy. This would make the night sky as bright as the sun. And yet, that is not what we see. The universe must therefore not be infinite, static, and eternal. Something had to change. And that change came over 200 years later, and as with many things in physics, it came from Albert Einstein. In 1915, Einstein published his brilliant theory of relativity, and in it he made a bold discovery. As an observer speeds up, time slows down and length contracts. The closer you get to the speed of light, the slower time ticks, until at the speed of light, if you could reach it, time stops altogether. Space and time are therefore innately connected. They are one and the same thing, and they form the very fabric of the universe itself. Space-time. Gravity isn't a force between objects, it's the bending of space-time itself by objects within it. The sun bends the fabric, and the Earth moves around this curved surface in an orbit. This was all good in theory, but they needed a way to test it, and 4 years later, they did just that. On May 29th, 1919, a total solar eclipse occurred, and it was visible from Brazil. Arthur Eddington organized 2 expeditions on behalf of the Royal Astronomical Society to image the eclipse. They were doing this to test Einstein's theory. If he were correct, then it wouldn't be just objects that move through this bent space-time, but the light itself should be bent and curved to move along this warped path. And since during an eclipse you can see the stars behind the sun, they could check and see if he was right. If his theory was wrong and the gravity of the sun doesn't bend the starlight, then they should appear to be here. But they weren't. The stars were here. They had shifted during the eclipse, being warped by the sun's gravity by roughly the same amount as Einstein had predicted. Einstein was immediately shot into stardom. The Times of London reported, "New theory of the universe, Newtonian ideas overthrown," and his name became synonymous with genius. Einstein's new laws didn't just apply to the gravity between objects either. They could be used to examine the fabric of the cosmos itself. While he had dethroned Newton with his new theory theory of gravity, he soon found himself faced with the same problem that Newton faced 200 years earlier. In general relativity, the universe was unstable. It must either expand or collapse thanks to the force of gravity. To try and solve this problem, Einstein modified his equations, adding in a value that he called his cosmological constant. It represents the energy of empty space itself. Basically, if you just took a box of empty space, how much energy would be in that box? He could then adjust this value to match the observations of the static universe. He would go on to call this his biggest mistake, but as we'll see later in the video, he might have been right all along. Okay, so around the same time that Einstein was figuring all of this relativity stuff out, astronomers had been turning their attention to the night sky, trying to solve one of the longest standing problems in physics. For centuries, astronomers had observed these fuzzy clouds in the sky. They called them nebulae, the most famous one being Andromeda. They didn't really know what they were. The philosopher Immanuel Kant described them as island universes, but we had no way of measuring how far away they were. That was until a brilliant woman, Henrietta Swan Leavitt, had made a breakthrough. Leavitt was a part of a small group of poorly paid female astronomers known as the Harvard Computers. She was tasked with measuring photographic plates to catalogue the position and brightness of stars. In doing this, she studied a special kind of star known as a Cepheid variable. These are bright stars that pulse regularly over periods that range from a few days to multiple months. She noticed a pattern. The longer the pulse, the brighter the star actually was. So astronomers could measure the period, figure out the brightness of the star, and compare that brightness with how bright they looked from Earth. Since faraway objects appear fainter, they could use that comparison to measure the distance to the Cepheid variable. Armed with this method, Edwin Hubble turned his telescope to the Andromeda Nebula and saw one of these special variable stars. He measured the period and calculated the distance to Andromeda. His result? 900,000 light years, well beyond the outer reaches of our galaxy. Those island universes exist. All of these fuzzy nebulae that we had been looking at actually were galaxies of their own, just like our Milky Way. In that instant, the universe as we know it increased in size by 1,000,000 times. Hubble had changed astronomy forever. Another astronomer, Vesto Slipher, had also been looking at these galaxies when he noticed something too. Most of them had their light redshifted, indicating that they were moving away from us at insane speeds, hundreds of kilometers per second. We now know that this redshift was caused by the Doppler effect. Building on this, Hubble used his new methods from Slipher and Leavitt to measure the distance to a number of galaxies and figure out how quickly they were moving away from us. He put all of this data onto a plot, and the trend was clear. The farther away the galaxies were, the quicker on average they were flying away from us. Exactly what we would expect to see if the universe was expanding. The static universe of Newton and even Einstein was dead. Hubble's observations had confirmed what other physicists had believed for a while now. Alexander Friedmann and George Lemaitre had been using Einstein's equations to predict a dynamic universe, and they were right. They immediately thought to turn back the clock. If the universe is expanding as time passes, when we move back in time, it should contract, getting closer and closer together until it reaches an extremely dense state. Lemaitre called it the Primeval Atom. He claimed that we were living in the smoke and ashes of a bright but very rapid fireworks. Lemaitre became known as the father of this new theory, somewhat ironically because he was also a Catholic priest. Remember earlier how I said space and time were innately linked, one singular space-time. This meant the beginning of space would also be the beginning of time. Stephen Hawking and Roger Penrose would later go on to show that this wasn't just an assumption either. Time really did stop at this initial dense state. They did this by taking Penrose's solutions for a black hole singularity, where there's infinite density and curvature at a single point, and applied it to the entire universe. They were able to show under a set of assumptions that the expanding universe we see today had to have started with a singularity in the distant past, a day without yesterday. This is probably what you were taught in school, that the Big Bang started from the singularity, but as we'll see, this is almost certainly not true. There was a problem with this primeval atom model of the universe. If you took the rate of the universe's expansion and just turned back the clock, you could figure out how old it was. And when they did this, the answer was an embarrassing 1.8 billion years old. Geologists at the time already knew that the Earth was at least 4.5 billion years old. So what's going on? Something had to be off. But to be honest, even without this problem, Einstein just didn't like the idea of an expanding universe. He had deep-rooted beliefs in his idea of a static universe, and so he began exploring a new theory that combined the primeval atom with his static universe. If the density of energy has to remain constant, he suggested that new particles of matter should be continually formed. He imagined a universe expanding without any origin, where the new particles could be created arising from his cosmological constant, the energy of empty space. The expansion of space spreads out the new matter, and so the total energy density of the universe is constant. Everything is solved. But he couldn't get this idea to quite work though. There were all of these small problems, and so he didn't tell anyone, and it was only discovered in his archives in 2014. Lucky for him though, 3 scientists in England had all thought of the same idea all the way back in 1945. Fred Hoyle, Thomas Gold, and Hermann Bondi thought up the same concept Einstein had abandoned. They called it the steady state model. These were the 2 big ideas at the time, the primeval atom and the steady state. Hoyle actually had a radio show and spoke about science in England, and one time he was on air describing the 2 of them when he referred to the primeval atom, saying all the matter in the universe was created in one big bang at a particular time in the remote past. The Big Bang name was born, and it stuck. We had the foundations of the Big Bang in place, and it probably sounds pretty similar to what you think the Big Bang actually is. A long time ago, everything was closer together and hotter, and then bang, the universe is born. But there was still testing to do. One thing that people were thinking about is what happens to all of the matter, the planets, humans, stars, galaxies, all of that, as they get traced back in time to the Big Bang. The physicists George Gamow and Ralph Alpha showed that as the universe contracts, it would get hot and dense, and eventually the matter would break down into a soup of protons, neutrons, electrons, and photons. So right after the Big Bang, everything was just this soup of particles. There was no empty space. It was so hot that the whole universe was basically just one big nuclear reactor. The protons and neutrons would snap together, forming the nuclei of hydrogen, helium, and lithium atoms. After about 5 minutes, everything had cooled down enough for this nuclear reactor to shut down. All of the atomic nuclei had been formed and locked into their exact proportions. Gamow and Alpha predicted that 75% of the nuclei would be hydrogen, 25% would be helium, and a tiny proportion of things like lithium would be found. Amazingly, they were right. Observations agreed with this ratio, and they didn't stop there. This team kept thinking about the early universe and their soup. 5 minutes after the Big Bang, and the soup was filled with basically 3 things: atomic nuclei, electrons, and photons of light created in the Big Bang. This light was continually being absorbed by the nuclei and re-emitted, flying around in the plasma because it was so hot. The soup would stay like this for 380,000 years until it had finally cooled to a nice 2,700 degrees Celsius. In that moment, everything changed. Immediately, the electrons snapped to the closest nuclei, and those photons of light were finally free to fly out through empty space. If you were there watching, it would have been a bright red glow, and ever since then, this light should have been traveling out through the universe, being stretched by space-time as the universe expands, getting redshifted so much that it should now be in the microwave end of the light spectrum, and extremely cold, around 2 Kelvin. They called it the cosmic microwave background radiation. If they wanted to once and for all prove that the Big Bang was real, they would need to find this light, and if they could do it, they would literally be taking a picture of the Big Bang. The hunt was on. By the 1940s, an astronomer named Andrew Mikael was studying clouds of alcohol in space when he measured the temperature of that empty space around the clouds. He found it to be 2.3 degrees Kelvin. So what was it? Well, he didn't know, and no one connected the dots. He was measuring the afterglow of the Big Bang and didn't even realize it. In the meantime, the steady state model was basically dead. The main problem for the Big Bang was this age problem. It predicted the universe was far too young. New data had shown that the original distance to the Andromeda galaxy was miscalculated. It was actually over 2.5 million light years away. So using this new data, the age of the universe was predicted to be 10 to 20 billion years old. The age problem was solved. Astronomers at Princeton had set their sights on the CMB, and they were getting close. They could feel it. But someone beat them to it. Just down the streets at Bell Labs, they had detected this strange hiss in their data. Arno Penzias and Robert Wilson couldn't figure out what it was. They tried everything to remove it, but to no avail. That's when they spoke with some people from MIT, and they realized what they were looking at. It was in fact the cosmic microwave background radiation, measured at 2.7 degrees Kelvin. They received the Nobel Prize for this discovery, and the Big Bang had its crown jewel. If we could see it today, as it were, when it was first emitted, and take a picture, it would look like a red glow in the sky from every direction. The light from the Big Bang itself. And it wasn't long until they did just that. Took a picture. By 1982, NASA had approved the creation of a spacecraft that would image the entire CMB. It could sweep the sky, mapping what it looked like in every direction. The Kobi satellite. And by 1990, they had all the data they needed and made their big reveal. The CMB in all of its glory. They had mapped the entire sky's contribution and had the most complete image of the CMB ever taken. Stephen Hawking declared the result the scientific discovery of the century, if not of all time. And it wasn't just beautiful, it confirmed something that scientists had suspected for decades. In physics, there's something called a black body. It's an idealized object that absorbs all light. 100% of it. All of that energy should then be re-emitted by the object in a perfectly predictable way. Its light spectrum should look like this. Depending on the temperature of the object, this shape could change, but there is always a perfect theoretical spectrum shape for the black body. They predicted that the CMB should have this signature of a perfect black body, and it did. It was the most perfect black body ever observed in history. Standing ovations, Nobel Prizes, and an accurate description of how the universe was born. So that's the end of the story, right? The universe starts with a bang and that's it. Well, not quite. There were 3 huge problems that were still left unanswered. The first is known as the horizon problem. We have since mapped the CMB to extremely high precision and measured the thermal difference across the entire sky, and it's nearly perfect. The entire signal is pretty much exactly 2.7 degrees Kelvin, no matter where you look. The problem is, there was nowhere near enough time for the temperature to pass from one side of the universe to the other and let everything come to a perfectly even temperature. Even traveling at the speed of light, there was no way that 2 points in the CMB from opposite sides of the universe could have thermalized in the 380,000 years before the CMB light was emitted. It would have literally taken trillions of years. And you might assume that the problem would be solved if the universe were just perfectly uniform right from the start. But if that were the case, we wouldn't see this abstract distribution of galaxies today. The second problem is known as the flatness problem. Space in the universe can have different degrees of curvature. The amount of curvature is given by a number called omega. If omega is 1, then space is flat. Parallel lines will stay parallel forever. If omega is less than 1, space is negatively curved. These parallel lines will diverge. And if omega is greater than 1, space is positively curved. Those very same parallel lines will converge. When we measure the curvature of space in real life, it's nearly perfectly 1. This prediction of a flat, expanding space is inherently really unstable. If there's any slight deviation from 1 in either direction, it would rapidly diverge away from that value, like a pencil balanced on its tip falling over. And since we measure it as 1 today, it must have been unimaginably close to 1 in the distant past. If omega wasn't 1, the consequences would be catastrophic. The universe could tear itself apart or collapse and destroy itself. So why is the universe so flat? The third is known as the monopole problem, and it was pointed out by particle physicists. At such high energies like those that would have been present in the early universe, a huge number of these strange particles called magnetic monopoles particles should have been formed. These are hypothetical isolated magnets with just one polarity, either north or south with no corresponding opposite. The problem is, we have never found even one, and they would have been so heavy that they would have prevented the universe from expanding. And beyond these problems, there was still the singularity. Most physicists felt something had to be off, that these were just artifacts of the mathematics. Einstein even called the idea that the universe started at the Big Bang singularity repugnant. By this point in our story, everything had started to come to a head. Hawking and Penrose's proof of the singularity hinged on 4 assumptions. Gravity is always attractive, the universe has 3 space dimensions and 1 time dimension, time travel into the past is impossible, and Einstein's theory of general relativity describes the evolution of the universe at all scales. And now, every single one of them is in doubt, especially the 4th. We know that GR has some big problems when it comes to those interactions where it disagrees with quantum mechanics. Both Hawking and Penrose have disavowed many of these assumptions. Their singularity proof that time started at the Big Bang had fallen apart. It's clear that we needed something more, something better than the Big Bang singularity. Our solution would come from a brilliant physicist named Alan Guth. Guth was thinking about phase transitions in ordinary physics, ice cubes turning into liquids as they melt. If you then heat it more, you get steam. These are phase transitions. But there are some strange kinds of phase transitions too. If liquid water is pure enough, it can be cooled down below the normal freezing point, delaying the phase transition in a process known as supercooling. In the Big Bang, it was thought that the universe cooled down from an infinite temperature as it expanded, but this cooling would give us the monopole problem. So what if we could delay it like we can with water? They calculated that if the cooling is delayed a bit, the monopole problem disappears. They just don't get created. The question then becomes, what does this supercooling do to the expansion rate of the universe? Well, you might think of empty space as, well, what it sounds like, just completely empty. But quantum mechanics has shown us that it really is a sea of chaotic activity. Hidden from us, there's a layer of quantum fields, each one corresponding to a specific particle. An electron field, a quark field, you get it. When there's a ripple in that field, we get the particles that make up you and I. Our electrons come from this underlying field. In this empty space, particles and antiparticles like electrons and positrons pop in and out of existence all the time, briefly moving apart before reuniting and disappearing back into the vacuum of the quantum fields. It's these quantum interactions that gives the vacuum of empty space a tiny little bit of energy. And remember, energy and mass are the same thing. So if you have enough empty space and can extract the energy from the vacuum, you can get enough mass to create you, me, or even the entire universe. Guth started to calculate how quickly the universe would expand if it were driven by the energy of this empty vacuum of space, and the rate was insane. The universe in a tiny fraction of a second would expand by at least 100 trillion times. He immediately realized that this insane period of growth would immediately fix the flatness problem. By using this period of rapid growth, the equations got flipped upside down. The value of omega, representing the curvature of the universe, was rapidly driven towards 1. No matter what shape the universe was initially in, the vacuum energy-driven expansion perfectly flattened out the universe. The flatness problem was solved. When he did this calculation, he knew he was onto something big. He wrote spectacular realization. This kind of supercooling can explain why the universe is so incredibly flat, and therefore resolve the fine-tuning paradox pointed out by Dick. The problem seemed to disappear like magic, all thanks to this period of rapid expansion. Guth named it inflation. The final problem inflation had to solve was the horizon problem, and it was actually quite simple. Since inflation grew the size of the universe by such a huge amount in way less than a fraction of a second, any 2 points that we see that were too far apart to be able to communicate and come to the same temperature in the old model would have started out much closer together. This gives them time for the photons to go back and forth and arrive at the same temperature. That's why the CMB looks so uniform today. The horizon problem was solved too. This theory of inflation was doing magic tricks. It solved the 3 most pressing problems for the Big Bang just like that, replacing the pesky singularity in the process. And that wasn't even its biggest triumph. When we look out at the CMB, we can see these areas that have a slightly higher density. There's a little bit more of that primordial soup here than in those cold spots. And since gravity always pulls more matter towards these overdense regions, these little variations explode over billions of years thanks to gravity, giving us the cosmic web of galaxies and structure that we see today. If the CMB were perfectly uniform, the universe would have no galaxies at all. Inflation is driven by the quantum inflation field, and these fields have built-in inherent quantum fluctuations thanks to the uncertainty principle. These quantum fluctuations get frozen into the plasma as the expansion slows down, giving us the variation that we see today. If it weren't for these quantum fluctuations during inflation, there would be no galaxies or structure in the universe today. Combining all of these ideas, we can finally piece together a complete view of what actually banged during the Big Bang. We start with empty space. No matter or light, nothing at all. But our empty space is filled with an underlying field, the inflationary field. This field forces that empty space to rapidly increase in size. If it started out to be around the size of a grain of rice, it would have grown to be bigger than our observable universe in less than a trillionth of a single second. Keep in mind, at this point there is still nothing, just empty space. And then inflation ends, and bang, just like that, all of the energy in this inflationary field of empty space gets immediately converted into the matter and light in the universe. This is the hot, dense Big Bang that you were taught about in school. The light we see as the CMB today, and the matter that forms every star, human, galaxy, all of it is formed from the vacuum energy in that moment. No need for any singularity at all. But here is the crazy part about inflation. It doesn't end everywhere all at once. It happens in patches. So while inflation might decay into matter and radiation, creating our universe and the Big Bang right here, it can continue inflating outside of our universe, spawning potentially infinite numbers of these Big Bang universes. And we just happen to be inside one of them. The multiverse is born. And that is the most widely accepted view of how the universe came to be. Probably not what you were taught, right? When I was taught it 2 years ago, it was said that inflation happened after the Big Bang. The singularity was still spoken about, and there was really no mention of the multiverse. So, case closed, end of story, right? Well, not quite. As you've seen in this video, the field of cosmology is constantly evolving, changing, and new theories are always popping up, claiming to have a better, more accurate description of the origin of the universe. While this theory of the inflationary Big Bang is currently the best we have, it doesn't come without its own problems. Some popular critics argue that inflation is just too flexible and not falsifiable enough. In science, theory doesn't mean just an idea like it can mean in everyday language. A scientific theory has to make predictions that can be tested using observations from our telescopes and detectors. But it also predicts the multiverse, something physicists aren't very comfortable with. And before you go commenting saying, physicists can't even agree what the Big Bang is, how are we expected to believe it? Slow down. There are things that we know for a fact to definitely be true. The hot, dense Big Bang, just meaning that everything in the universe used to be really close together and much hotter than it is today, definitely happened. We can literally see it. That is not up for debate. But looking beyond that and trying to answer questions of what caused that hot dense state and what came before it is what's still undecided. The research for this video was largely based on a book called The Battle of the Big Bang. The authors attended a conference about black holes and fundamental physics, where all of the attendees are at the cutting edge of this field, and surveyed them about what they believe to be true about the beginning of the universe. When they asked them if they believe that the Big Bang was the beginning of time, the majority of them actually agreed it says nothing about when time in our universe began. Alan Guth, the father of this inflation idea, said the Big Bang theory was never actually a theory of the bang. It says nothing about what banged, why it banged, what happened before it banged, and that's probably a good way to think about this description of the Big Bang. I put out a poll on YouTube and Instagram asking people who didn't believe in the Big Bang to tell me why, so hopefully we can try and answer some questions. After looking through thousands of responses, it seems like there were really 3 main problems that people have with the Big Bang. The first is, why did the universe start from a singularity, that point of infinite density where all the matter in the universe was supposedly contained? If there is one single thing that you take away from this entire video, let it be this. This idea of the singularity is largely dead in cosmology. That's just the truth. We don't believe that the universe started from that singular point of infinite density anymore, but it does tell us something interesting. The singularity idea is just a prediction of how the universe starts if Einstein's general relativity is always true. And we've shown that over the last 50 years, that is not true. There's a huge disagreement between relativity and quantum mechanics that we need to solve. That's the theory of everything that everyone is searching for. But since we know that that problem exists, the singularity isn't accepted anymore. We need something better, and that's why we now have inflation. The second is, how can something come from nothing? Matter cannot be created or destroyed. Now there's a few things to say here, but it all hinges on this. Most conceptions of the Big Bang today don't claim that the universe came from nothing. And this idea that is taught in high school physics about energy can't be created or destroyed is a huge oversimplification, frankly. That rule is true, but it's constrained within our space-time and is subject to something called time translation symmetry. Since the space-time itself is expanding and changing all the time, this idea of global energy isn't actually even well defined. And then there's the quantum fields, the particles and antiparticles seemingly being created out of thin air. Basically, at the cutting edge of physics, a lot of these rules are more bendable than you were taught in school, and that's okay. And probably the most common response I got was the Big Bang cannot be true because if it is, what happened before the Big Bang? Again, this feels like more of a fundamental misunderstanding. The Big Bang models don't really claim to know what happened before the Big Bang. It's really that simple. But I would argue that your insistence that something has to come before the beginning of the universe is just a misunderstanding of how time works. Time is much more of a physical thing than it feels like. Our everyday experience makes it seem like time is just this thing that ticks by infinitely into the future and infinitely into the past. But that's just not true. If space-time itself didn't exist sometime in the past, then yeah, there was nothing before then. Very literally, but we don't know that for sure yet. I could talk for another 2 hours about all the different ideas people are developing to replace inflation, and if you want, I can make that video, just let me know down in the comments. But for now, that is where it stands. The singularity is basically dead. Inflation is our best model of how the universe came to be, and it's really successful. But there are still problems that we have to figure out. This is the hardest problem that humanity can even possibly try and conquer. The origin of the entire universe. It was never going to be easy, but I hope you can see how truly amazing the progress we have made so far really is. And now you understand the Big Bang better than nearly anyone else on the planet, even people studying physics today. If you enjoyed this, please do subscribe. I literally spent months working on this video and only 20% of you are actually subscribed. Thanks again to Planet Wild for working with me on this project. They're genuinely doing amazing work. If you want to see them in action, check out their project Protecting the Amazon.